Let's look at what happens when you connect batteries in different ways. So just like when it comes to resistors, we have two kinds of connection. We have series connections when batteries are connected end to end this way, and we have parallel connection when the batteries are connected across each other this way. And what we will see, and we'll discuss this throughout the video, is that in series connection, we will find that the batteries end up giving you more voltage, all right? And in parallel connection, we'll see we end up getting more current, and we'll clarify what that means. So in this video, let's focus on the series connection and see how we get more voltage. And in the next video, we'll focus on the parallel connection, see what it means to have more current, and we'll compare them, all right? So let's start by focusing on the series connection in this video. All right, so why is it that in series, when you connect batteries in series, you get more voltage? Well, let's think about this. Let's start with something that we already know, and we've seen before that batteries have something called an EMF. And let's say, for example, this battery has an EMF E1, which is 5 volt, and this one has an EMF of, let's say, E2, which is, 7 volts. So let's try answering this question. What would now be the effective EMF of these two cells? In other words, what I'm asking is, if I were to replace these two batteries with one single battery, what would its effective EMF be? What would the EMF of this battery be so that it's equivalent to two batteries? Does that make sense? Just like how we do it for resistors. So how do we figure this out? Logically, without having to do too many derivations, logically, how do we figure this out? For this, we need to recall what's the meaning of EMF. And we've talked about that in previous video, but let's just jog our memories, okay? The idea behind EMF, or the way I like to think about it, is batteries, what do they do? What's their job? Their job is to push charges, think of positive charges. In reality, it's electrons, negative, but it's easier to think in terms of positive charges. So their job is to push positive charges from negative to positive. So let me bring in a positive charge over here. So the battery's job is to act like a pump and push them from negative to positive, push them from negative to positive. And the EMF represents how much energy the battery delivers to the charge per coulomb. For example, 5 volt means when the battery pushes it from its negative to positive, it delivers 5 joules of energy per coulomb. If this was 1 coulomb, it transfers 5 joules of energy. And similarly, what does this battery do? When it pushes it from negative to positive, it transfers 7 joules of energy per coulomb. So if this was 1 coulomb, this battery would transfer 7 joules of energy. And if this concept of EMF is not clear to you, or you need a refresher, feel free to go back and watch our videos on EMFs, internal resistances, terminal voltage, and then you can come back over here again. All right. So now the question we are asking is, what is the effective EMF? So what would be the EMF of this effective battery? So let's call it as ES. What would that be? So what we're asking is, if I were to take the charge 1 coulomb from here to here, how much energy would get transferred to it because of these two batteries together? That would be the effective EMF. Does that make sense? So can you pause the video and think about, based on what we just said, what would be the effective EMF? All right, hopefully you've tried. So we know that when a coulomb goes from here to here, it gets 5 joules. And then when it goes from here to here, it gets another 7 joules. So what is the total energy transferred per coulomb? That's 5 plus 7, that is 12 joules. And so the effective EMF is 12 volt. And as a result, we can now hopefully see that the effective EMF in general, so S stands for series, effective EMF, is just the sum of these two, E1 plus E2. And if there were more cells connected in series, I hope you agree, there'll be just E1 plus E2 plus E3 and E4. And this is why I said in series connection, you get more voltage out of it. So whenever you require more voltage from a battery or multiple batteries, you just put them in series. Now, one thing to be careful about is, notice, to get more voltage, look at the connection. The positive needs to be connected to negative. That's how the connection needs to be. All right. Now, my question to you is, and I want you to think about this, what if we didn't connect it that way? What if we connected it this way? What if we connected positive to positive or negative to negative? Can you now think a little bit about what would the effective EMF of this be? Use the same idea. Think logically, and then think about what that effective EMF is. Yeah. So can you pause the video and think about this? All right. Let's see. So I'm going to bring this charge, and now I know that when this charge goes from here to here, the battery pushes it, and provides 5 joules of energy per coulomb. If this was 1 coulomb, it transfers 5 joules. But what happens when the charge goes from here to here? Now notice it's going in the opposite direction. It's going from positive to negative. And when that happens, it loses energy. Now you can imagine the battery sucks energy out of it. So how much energy is being sucked out of this charge now? Not sucked out 7 joules. So think about it. When it goes from here to here, it gains 5. It goes from here to here, it loses 7. So by the time it comes here, it has a negative 2 volt. So we can say the EMF, the effective EMF of this is negative 2 volt. And at this point, you might be a little comfortable. Like, what does it mean to be negative? Well, it basically is talking about the direction of the battery. So here's what I mean. So since I know that this side, I'm getting less than 0, you can imagine that this, oops, 1 second. This is the positive side of this effective battery, and this is the negative side. And that makes sense. This battery is dominating, so the terminals will have the polarity of this battery. And so that basically means now your effective battery should have a positive here, negative here. So your effective battery would look like this, and its net EMF is going to be, ES is going to be 2 volts. So I've already taken care of the negative. Negative basically means flip the battery. So 2 volts. And so it's not going to be always more voltage. It'll get more voltage if you connect in the right way. And when I say right way, you connect positive to the negative, positive to the negative. And we have seen that batteries have something called internal resistance. And what's the idea behind that? That basically means when the battery is pushing the charge and transferring, say in this case, 5 joules of energy per coulomb, not all the 5 joules get transferred to the charge. Some of it gets wasted as heat. And that's due to the internal resistance. A lot of internal resistance means a lot of heat gets generated. And so that's also an important factor. And so the question now we have is, let's keep the charge aside. Okay, so the question now is, if I know the internal resistance of this cell, let's call that as R1, and if this has an internal resistance R2, what's the internal resistance of this effective cell? What's the total internal resistance? Again, can you pause and think about this? I'm gonna give you a clue. You already know what happens to resistances when they're connected in series. So it's gonna be the same thing. So pause and think about this. All right. We've seen that when resistances are in series, they just get added up. That makes sense again, right? When the charge goes from here to here, it encounters this resistance and this resistance. So the total resistance becomes R1 plus R2. And as a result, the total resistance, the total resistance or the effective resistance is going to be R1 plus R2. What about over here? What do you think will happen to the effective resistance over here? Will it be subtraction or will it add up? Well, it doesn't matter how you orient the batteries, the resistance will always add up. Resistance don't have a polarity. So regardless of how you connect the batteries, the resistances will always add up. So long story short, if you want more voltage from your batteries, you connect them in series. Their EMFs get added up, provided you connect them the right way, but their internal resistances also get added up. In the next video, we'll look at what happens in parallel connection.